In the last class, I explained about the calibration without discrepancy. I will explain about what is this discrepancy in this class. And anyway, it was about the topic without discrepancy. And for that purpose, I introduced a small example, chemical kinetics model with this. And we assume that we have the true model in this equation. And we made virtually experimental data. And the result was like this. 3 replications at a point with the 11 points in the interval from 0 to 3. And using this data, we studied what will be like calibration without discrepancy. And at first, what I did was a deterministic calibration using the optimization to minimize the difference between the model and the experimental data. We find a deterministic value for, in this case, theta of the computer model. And on the other hand, in the probabilistic approach, we used the Bayesian method. And this is the result of the deterministic calibration. And the result was given by the blue curve in that figure. And that result was the result of the making the optimization. So best results with a single parameter theta to match the model as closely as possible to the data. But you still see there are some big difference between the model and the data. And in the probabilistic approach, we did the same thing. But in this case, the estimation is given by the distribution instead of a single value. And that was made by the Bayesian approach. And in that case, we have the unknown parameters to be calibrated, which are the parameter theta. And also, in this case, we will estimate the observation error, sigma, together within the Bayesian framework. And what we obtained was the posterior distribution for the 2 parameters. One is the calibration parameter. The other is the measurement or observation error. This is the typical example of the Markov chain Monte Carlo iteration, trace plots, and histogram. And what we obtained from that was in this figure, the pair of the red curves represents the upper and lower bounds of this computer model. Remember that we have now not only a single value of theta, but also we have a large number of samples for theta. So we can make the same number of response y. That means this is also in the form of distribution. So we can make the upper and lower bound for this. And this is the result, the pair of the red curves. And on top of this, we can also make the prediction of y by adding the observation error. In this case, this observation error is also in the form of a distribution because the sigma was also used as the unknown parameters to be estimated. And the sigma is given in this histogram. So we have this many number of standard deviation. Apply this to here, and as a result, we have the same number of predicted y. And the result will be this, a little wider version of the output. So whenever I come across this, I always emphasize the meaning of the difference between this and this. So I hope the students can distinguish the meaning of these two. Okay? So move to the next part. As a result, whatever the method I chose, the result I got was this kind of curve. And in this case, in this particular example, we already know what the truth is. The truth is very, I'm sorry, but it's not easy to identify the small dotted black line. And the virtual experimental data here. The main trend, mainstream of this direction is substantially different from what I estimated using my computer model. That means the computer model itself was not good. And the result we got was the estimation, calibration based on our computer model, which was a little bit wrong. And what we got was, due to this, we ended up with the large bounds of the uncertainty, upper and lower bound. And this is not satisfactory to me. So we'd like to make some improvements by introducing what they call the discrepancy function. And I will talk about this today. So the title is, of the today is calibration with discrepancy, by including discrepancy. And as I am getting closer to the end of the lecture in this semester, I am less using the standard textbook. Instead, I am more relying on the papers, articles in the journals or literature. That means that this is no longer any established topic. This is a kind of at the front of a research direction already. So it means that I am having a more hard times, difficulty in preparing the lecture in addition to my communication problem. So from today's lecture, there may be some kind of my personal interpretation, because this is you cannot find any the similar subject in the standard textbook. I have heavily used the papers to prepare today's lecture and the remaining lecture of these papers. The first two addresses the theory about the calibration, particularly the Bayesian calibration. Third one, kind of a follower of this paper. You can see the dates. It was published lately. So some kind of a different version and a little easier understanding of this subject. So all three, I would say, belong to the theoretic subjects. And the fourth and fifth, originally it appeared back in 2002 with a collaborated effort by Statistical Science National Lab and the General Motors. So this put more emphasis on the applications. And interestingly, later on, these authors made publications by separating out of their reports, one for the spot welding, and it is in this paper. The other for the car crashworthiness problem, and it was published later. So separate version of papers. These two papers are separate version of the original 2002 report. This one, by chance, I found this paper on the internet. Much easier explanation about the whole thing. I like the kind of this paper. The title says it, Calibration Tuning in Practice. So if someone is interested in this topic, I recommend to at first read this paper. And the last one address some more advanced topic by this author. He is now in the Sandia National Lab, and he was formerly a PhD student under Professor Mahadevan, and a very good paper to read. So I repeat why we need to introduce discrepancy. When I say discrepancy, I use in mixed way the other words, the inadequacy or bias, the same thing. When I say that those things, it will represent the same thing. And as I said before, accounting for this is very important. Every paper emphasizes this in the papers that I introduced in the last slide. And if we ignore this, and we already experienced in our small example, we will get unwanted large bounds in the prediction. So that makes us to include this into the calibration. And the answer is, when it comes to this bias function, we always consider employing this, the Gaussian process regression, to express this discrepancy. In that case, what we do in the calibration process is not only including the original parameters, theta, also we have to include the associated parameters due to the introduction of this. As a result, when we have obtained the bias function, we can use it for two purposes. One is we will use this to close the gap between the model and the reality. And this is the original purpose. The other purpose is use this as a validation of the model accuracy. If we end up with a large discrepancy function, that means that we did something wrong with the original model. If we end up with a very small, almost zero over the range, we have an excellent model, and we are happy with that. So for that purpose, this can be also used. Here's the formulation. I think this is very easy to follow and understand. We have the computer model with the parameters, and I denote this as this. X is the input variable, and theta is the unknown parameters we'd like to calibrate. And we don't have the model accurate enough. We are not sure, so we add some discrepancy term here. And by adding this, we will have a reality, a real model. And in the mathematical expression, this is given here. And in the field data, we will obviously have the observation error. And the equation is given in this form, epsilon. And epsilon is always assumed as the what they call, in the statistical community, they use this terminology, independent and identical error. So over the interested range, we assume that the error is independent and identical with the standard deviation sigma. In terms of the figure, this can be explained this way. We have the field data. We have the model somewhat incorrect or wrong, the green curve. And we will find soon there is a bias or a discrepancy between this model and the reality. And this will be something like this. And on top of this, we will have the measurement error. And the results will be given, for example, like that figure. Within this formulation, the things we need to estimate, we have many in this case. The first one is the original calibration parameter in the computer model. The second one is because I introduced the Gaussian process for the bias, we need to estimate this too. The third one is this one, the observation error. All these should be estimated in the Bayesian framework. As in many cases in my lecture, I like the procedure like this. I will also explain the process by increasing the order of the complexity for this process. So at first, I will focus on the bias function only. That means that we already know the parameter theta. We don't estimate it for simplicity purpose. In order to explain the thing to the students, I will assume this as known. Also, I will ignore the observation error, unnecessary complexity. So we will totally focus on this as of now, at this stage. Then we move to the next stage by including the observation error. So in this case, we will estimate the parameters here and the error sigma together. This is the next phase. And the final stage, we will include all the parameters and estimate it. The first case, the problem is given here. We have the math model or computer model. We have the parameter theta, but in this case, we assume theta is this value. Also, I said there is no measurement or observation error for this specific case. In that case, that means the sigma is already 0. In order to make this, we have to know this thing, because the field data, originally I showed you there are 3 replications at a point. In that case, we cannot say there is no observation error. So for this purpose, we use only one data set at a point. And the result will be like this. Originally, we saw 3 data sets at a point, at every point, but in this case, I use only one. And in order to make the Gaussian process regression, we need to change from the original to this. Very easy. The field data here denoted by blue squares, this is composed of the computer model plus bias. And the computer model, we already know this with this value. So move this into this side, and we will get the bias data in this form. And the bias data will be given in these blue squares. And we'd like to make the results that can approximate this data using the Gaussian process regression. And the result will be something like this. And for the Gaussian process regression, I already addressed some weeks ago in the 10th lecture note. But at that time, it was not good to explain. And I still have difficulty. Whenever I come to across this issue, Gaussian process, it is always difficult to explain. I briefly explain once again what it is here. When we would like to make an approximated function for the data that we saw, the data, when I say data, the data means here, this data. We'd like to make approximated function that can cover this data. Using the Gaussian process, it means that the function is modeled by multivariate normal distribution. Here, this is the mean. This is the covariance matrix. And the mean represents or responsible for the global variation. Typical is the polynomial regression. But 99% of the case, they don't use the polynomial. They just introduce the constant, the simplest case. In that case, f becomes unit value. The correlation matrix. This is responsible for the smoothness between the points. At that point, at each experimental point, we have the value, so there's no problem. In between those points, how do we connect? How do we make the approximated function? This is responsible for that. And we have to pay attention to a parameter called the correlation parameter, H, here. And this is responsible for the degree of smoothness of that approximate function. And I'd like to say that if the matrix is changed to diagonal, yes?
What is F?
Large F.
Well, what is it? Like, see, so it says mean F times beta. You can take it to be constant if you have F equal to 1. So what does F represent?
In the regression, classical regression, I hope you remember the regression model will be something like this. Or you can add, if you like, whatever. In this case, I consider the regression as this.
Okay, so F represents like the number of betas that you're going to have.
So F represents the, in other terminology, F is also given by the trial functions.
Like the monomial that we use for the X super M.
Super M, I don't know what it means, but Professor HAFTKA may have taught you about that.
So in this case, F is a scalar, so
something like that. Yeah. That can be interpreted in very many different ways. Another different interpretation is given by Chanyo. Yeah. So if we change this complex structure into the simpler one, the diagonal unit matrix multiplied by a scalar sigma b, in that case we will get to the arrive at the ordinary classical regression. Using this, it becomes Gaussian process. Using this, it becomes an ordinary regression. That's the difference. The characteristic of a correlation matrix represented by this form, as we have a larger h value, we will have a wider shape of the correlation function. As we have a smaller value, it will be something like a narrowed down shape. The meaning of this is, let's consider a points with the, if we have a large h, that means we will have a high correlation for at the 2 points. When I say 2 points means xi and xj, it is separated with a distance. For those 2 points, in case we have a large h, then we will have a high correlation for y's. That means the two y's will not differ much. If y has a value of 3, this y should not have a minus 3. This y should have a value close to 3. The meaning of this correlation is that. And if h is small, on the other hand, the opposite case. In that case, yi and yj can be independent of each other. So any value can, any yj value can take, independent of yi. So you understand the meaning of this in that way. At the same time, we can also say that at the point close to the observation, we will have a high correlation regardless of h, because xi and xj is very close each other. So we have a high correlation. In that case, another y at another point, very close to the observation points, will not differ much from that observation. So this means we will have a small uncertainty close to the observation points. At point itself, the uncertainty goes to 0. So this is the overall meaning why the Gaussian process always interpolates the data point instead of approximating. Okay, I have to move to the next issue. And this is the detailed process of a Gaussian process regression. As first, we make a likelihood expression for the field data based on the given parameters. And once we have this expression, we can multiply prior of these parameters to this expression to obtain the posterior. And there is an analytical solution in case of non-informative prior. And the result is this. And once we have the distribution for the unknown parameters, we can use this to have the posterior prediction. This is a typical of a Bayesian procedure. So apply this method to our example. Our example is about this, the bias data. Originally, what you see was this original measurement data, but in this case, we will use this data for the Gaussian process. With a small h, and by increasing h, we get the results of the Gaussian process. And what you get from here is with a small h. In that case, we have a very small correlation. And the response, or y, will be independent each other. Even at the point close to the observation points, they will be generated independently based on the error we made. So the result will be something like this. And yeah, it's not easy to explain this. If the h is smaller, the global trend will be close to the ordinary regression. In this case, the ordinary regression is just a constant value. So we have the constant value. Only near the observation point, we have the interpolation to that point, but otherwise, we have the global regression model from this figure. As we increase this, like h equals 0.1, we have a result like this. The blue curve represents the mean of the Gaussian process model. And the pair of the red curves represents the upper and lower bound. And that represents the uncertainty due to the approximating, making the approximation of the functions based on the data. If we further increase to h equals 0.2, we will have a better smoothness in the Gaussian process and smaller uncertainty bounds. There is another method about how to impose h, the correlation parameter. In my case, I just used an arbitrary values from 0.1, 0.01, 0.1, and 0.2. But in many literature, h is obtained by using the maximum likelihood estimation method. And by going through that process, you will get the value of this, 0.416. But in my implementation, this didn't work. There was a singularity during the MATLAB computation. So I don't know why many literatures are emphasizing this approach. So that is my difficulty in practice. In my case, so I just use the h at 0.2 in the remaining process. So this was the results without observation error. But in fact, there are observation error, and we need to include this error too. So from this time, I will add this error in the estimation on top of the Gaussian process. This is something like this process. In the ordinary or classical regression, what we did was we set up the formulation like this. This is the regression. This is the observation error. And after going through the Bayesian process, what we get is the uncertainty of the regression parameters, uncertainty of the error. So we will have the upper and lower bound of the regression, and also the upper and lower bound of the prediction by adding this observation error. So this is the thing when we go through the classical regression. We do the same thing. This is replaced by the Gaussian process. And on top of this, we add the observation error. In that case, we will have to add something like a nugget term. And this is explained in the next slide. All the other process is the same. We only add this term into the correlation matrix. And we do the same thing. But instead, in this case, we have one more unknown parameter, which is the observation error. Previously, we did not consider this one. So the result we got was always the interpolating, passing through the data points. In this case, the thing is different. In this case, we will not pass through the data points. We even have the replications at a point. That is never possible. The Gaussian process originally penetrates the data point, but in this case we have 3 replications, never possible. So we need to, by whatever way, have the approximation of the Gaussian process. This is the procedure. And this is the results by a smaller h value and a 0.1 value and the result of the 0.2 value. And with this smaller h value, we have a very small correlation. So at the points not close to the data points, we have independent behavior. So the results will be like this. And the global mean is some kind of a global mean of the data set. As we have the higher correlation parameter h, the results will be like this. And h at 0.2, we get this result. And this red pair of the red curves represent the upper and lower bound of the Gaussian process. Use this to the original figure by adding the computer model. Remember that we don't have any uncertainty. We already know this function. So we can add this to these results and get the lower part of the figure. And the thing is this. And in this figure, I add another pair of curves, magenta color. This represents the predictive uncertainty. Within this, the red part is the uncertainty of the Gaussian process itself. The magenta color includes the observation error. I just show you the comparison. In case we had only one data at a point, and we went through the ordinary Gaussian process, the result was this. Now we have replications. We cannot make the thing like this because we have multiple data. In this case, we introduce observation error. In other literature, they call this as a nugget term. In that case, we will end up with the approximation like this. The red curve is a mean of the Gaussian process, and the pair of the red curves is the upper and lower bound. On top of this, we add the observation error, we get the magenta color. Also, I'd like to remind you what was the result when we had the, in the previous lecture, when we did not include the discrepancy. We just used only the computer model. In that case, the result was this. We had a large bound of uncertainty due to the bad model. And what we got here, by adding the bias, we got, how do I say, substantial improvements with the uncertainty. To some people, it could not be said like that, but there is a improvement, a reduced uncertainty, upper and lower bound from here to here by introducing discrepancy. This is the last one. In this case, all the parameters are used for the estimation. But the thing is, only we add a theta in this small example because the calibration parameter is theta 1. So previously, at this location, we had the bias data, and we already knew this value. Now, it is changed into the unknown. Only this is known. So with that understanding, the remaining process is the same. And we have 4 unknown parameters in this case. And go through the Markov chain Monte Carlo. And let it estimate in the form of a distribution. And the result is this. In the order of this, theta, observation error, sigma, and bias or discrepancy, beta, and its correlation parameter, sigma b. We have the results for all of these parameters in the form of samples. But the thing is, in this case, is when we make a scatter plot of sigma and beta, we see the figure like this. This represents that there are the relation between the 2 parameters, the calibration parameter and the bias parameter. And this can be easily understood that because the reality is given by the summation of the model and bias. If we have a specific model value, we will the corresponding bias. So whatever value we have for the calibration parameters, we can also have the corresponding bias function. So statistical terms, this is also called the 2 are confounded. We cannot identify the unique values independently. So they are not statistically identifiable. But the prediction, which is the summation of the 2, in that case, we don't have to care about the accuracy because whatever value it takes, after summation, we will have the same result. So in practice, whenever we run the process, Markov chain Monte Carlo, we have the different results in terms of the theta and bias parameter, beta. Theta, beta. Theta, beta. Always different whenever we run a simulation. The others, pretty much less variance. In this case, ignore the red curves. In this case, the mean of the calibration, the mean of the computer model is given by the green curve. Mean of the bias function, which is a Gaussian process, is given by this blue curve. And as a result of accounting for all these, we get this result. In this case, quite different case, opposite case, we have a bias like this. And the computer model is given by this. But the results will be the same. Another attempt. So I am showing you 3 different results as a result of the Markov-Chain Monte Carlo. And whatever result we take, the ultimate prediction result will be given in this form, the same similar result we get. And you can compare this with the result without discrepancy. This is the result with discrepancy. And this is the math computer model. And the blue curve is the mean of the bias-corrected reality. And it goes through in the middle of the data. And the red 2 curves represent the confidence bounds of that model. And the magenta represents the prediction. Yes, this is the end of my lecture today. And some parts I was not good to explain. I will welcome your question later. Still, I am having many questions from the students through the email, and I am responding to every question. Also, there is a MATLAB code exactly representing that results. So anybody can try themselves. And the code will be explained in my last recitation planned on Wednesday next week. Okay?